There you go. Hi, everybody. With that exciting moment uh, today, maybe with some, significant ambition, we're going to work on the question of how can we trust machine learning. And as Ravid said, I recently joined Stanford University, and they invited me to apply there. And as part of the process, they wanted my teaching evaluations for all the classes I've taught over the last 20 years. And I strategically hit this one. It said, from back when I was a professor at Carnegie Mellon, it said, Professor Gestrin, I'm very disappointed in your class. I thought machine learning was going to be magic, but it's just math. And this is what I call the myth of math in machine learning, where the idea back then was if you take data and you do some machine learning math magic, you'll get profit, which to me meant showing that my curve was better than your curve and then writing a paper about it. Now, this might be naive, but there must be some magic in machine learning, since it's changing the world, solving problems we never thought before, like self-driving cars or helping us live a healthier, happier day. And to me, the magic in machine learning is really in the spaces between the math, how we define the problem, how we collect data, how we define our models, integrate into an overall application and system, and overall, how do we evaluate these approaches in every step of the way to make sure they're solving the problem we would like to solve. Now, to me, there is math, but it is a small component in the overall picture. And this picture is filled by complex human decisions that are getting harder and harder, because as machine learning is making more and more decisions for us, and the systems are getting more and more complex, it's natural for us to ask the question of how can we trust machine learning? And to approach this question, I asked myself the perhaps harder or simpler question, oh, how can we trust? And I read a lot of literature in this space, and I'm inspired by this work in medicine, the seminal work, that said that when you trust your provider, your doctor, you have increased adherence to treatment and continuity with that doctor. But when you don't trust them, there are low rates of care seeking, preventive services, and going for surgical treatments. And they identified 3 areas of trust in the medical domain. Technical competency, does my doctor know what they're doing? Interpersonal competency, does my doctor communicate with me well with respect to what they're going to do? And agency, does this doctor have my best interests in mind? So with that, I ask myself the same questions. What are the core principles of trust in machine learning? And I'm postulating 3 core principles, which I'm going to talk to you about today: clarity, competence, and alignment. Clarity is the quality of being easily understood, which we know it's really hard for a lot of machine learning systems and methods. Clarity to me has a lot to do with interpretability in ML. So the question here is, how do you give humans a mental model of how the machine learning system works? Now, we can do this in various ways. You could pick a very simple model, like a shallow decision trees or a set of if-then rules, and it's really easy to understand. But the problem is their accuracy tends to be very low. You try to make them more accurate, you add more if-then rules, deeper decision trees, and it gets harder and harder to understand. There's been a lot of work on trying to find more interpretable models that are more accurate, but they still don't reach the state-of-the-art accuracy that we see in real-world use cases or human-level AI. And so our goal is to focus on the most accurate models and try to increase the interpretability of those models. The way we approached it when we started this journey is by saying, let's consider the models a black box. In other words, we can explain any machine learning model. We're model agnostic. We can explain state-of-the-art models. We can explain current models and future models you're going to come up with. We can compare 2 models from different model classes. Is that even possible? So the approach started with a very simple idea, which led to thousands of papers in this space. The idea was, if you take a prediction that you make, it might be a very complex decision boundary. But if you zoom in and zoom in some more, you see that locally, it might be simple, maybe even well approximated by a line. So in our first paper in the space, back about 5 years ago, we proposed finding sparse local explanations around each prediction. Let me show you an example of that. If you use an image classifier for this input, it gets confused, but it says it's an electric guitar with probability 32%, and Lime says it does that when it looks at this part of the image. It's an acoustic guitar when it looks at this part of the image, and it's a Labrador when it looks at this part of the image. And what we showed is that making models more interpretable and highlighting what's important for a decision can give humans a successful mental model of how these machine learning models behave. Now, Lime explored linear explanations around each prediction. There's been a lot of follow-up work from that. From my group a little bit, from others a lot. But let me just show another example to give you a sense of a range of what's possible, and then it will motivate the rest of the presentation. Another question we asked was, what are sufficient conditions for a prediction? In other words, what's the region in the space that if I were to move the input around in this region, nothing would change, the prediction wouldn't change. So here's an example. If you give me this image for image classifier, it's a beagle. And on the right, we're showing the parts of the image that if we keep constant, it will change anything on the rest, move it around, it will still think it's a beagle. Those we call anchors. Let me show some other examples of that. Take a task called visual question answer. It's an amazing task. You give me this image and you ask, what's a mustache made of? It says banana. Amazing. Or how many bananas are there in the picture? It says 2, which is pretty incredible prediction. However, if you look at the anchors of those questions, for the first one, it's just the word what. And for the second one, it's just the word many. So in other words, any question with what will get the answer banana. Like, what is the ground made of? Banana. What's the hair made of? Banana. What was the head of the US? Banana. You get the idea. For the second question, it's many. So any question with many gets the answer too. Like, how many are in the picture? 2. How many is too many? Obviously 2. And so clarity helps humans have a mental model how the machine learning model works, helps us understand when it's working for the wrong reasons, and help us make more informed decisions if we're taking these models and using them as part of a complex decision-making process. And here's a really cool paper that we were not part of, where they use similar ideas to help prevent hypoxemia during surgeries. And here, just predictions from models were sufficient, but explanations help doctors make better decisions in the operating room. So clarity is fundamental, in my opinion, to gain trust about models. But a second quality that's incredibly important is competence. Competence is the quality or state of having sufficient knowledge, judgment, skill, or strength as for a particular duty or in a particular respect. In other words, you must have sufficient skills for the task that we're trying to solve. Here, I talk about competence in machine learning as being measured through evaluation. In the 2008 teaching evaluation that I got, competence was simple. My curve was better than your curve, and my paper got accepted. But even this notion that there's a benchmark data set or a fixed data set is extremely naive in practice. It's really hard to get test sets that are representative of all the aspects of the world that we really care about. And we think we need more thorough ways to evaluate and test machine learning models. And here I advocate a software engineering perspective to taking this on. And I propose, for example, here today, 2 types of techniques, failure analysis and systematic testing. Let me give you some examples of that. Failure analysis is about finding ways that you can perturb the input that's going to break your models, change the predictions. And folks have studied this in several ways. One way is to say, here's an input, add an imperceptible bit of noise, and it changes the prediction. This is pretty interesting and cool, but it's generally only applicable for security type settings because this noise is imperceptible and it's not natural. It's not what we observed in the real world. Here are some natural examples. They're more perceptible. Take the visual question answering task. I give you this image, you ask, what type of roadside is shown? It says a stop sign. It's amazing. Or I give you this paragraph and it says, how long is the Rhine? It says 1,230 kilometers long. It's pretty amazing. However, if I change the first question from what type of roadside is shown to which type of roadside is shown, now it's do not enter. Or if I change the second question from how long is the Rhine to how long is the Rhine? By adding an extra question mark, now it's 1,050,000 long. And these types of brittlenesses in machine learning systems for inputs, they're natural in the real world, are very significant, need to be detected, they need to be addressed. So one of the approaches that we did was to look for the semantically equivalent adversarial examples. So the idea is to use paraphrasing models to find alternative inputs and then find ones that break the model. So for example, for this image, if I ask what color is the tray, it says pink, which is really cool. Now we do some paraphrasing and I say, what color is the tray with a British accent? And now it's green. Or which color is the tray? And now it's also green. And so we found that such natural changes would break the model. And the question is, what do you do with that? And one thing that you can do that's pretty simple and natural is to find these failure modes and use them to augment the data and improve the coverage of a model. And if you do that, you can significantly improve the robustness of these machine learning systems. So machine learning systems are prone to such bugs, and we must focus on semantically meaningful issues that will make a difference in the real world. Now, even if you do that, we might ask ourselves the questions of when do you think we're ready to really ship a machine learning model? And to this, I say we should test models like we test software. And as an example of that, recently we published a paper called Checklist, which is about a methodology to test, in this case, NLP models, but generally machine learning models. Let me show you a simple example. Let's work with sentiment classification tasks. So for example, you take the input, easily the best airline in Seattle. I guess I recently moved, so I should say easily the best airline in San Francisco. And you give it a sentiment classifier, and it says it's a positive, neutral, or negative sentence. How do you test such model? You should start with core principles. So small test units, for example, on a variety of areas that are important to the model, like vocabulary, naming entities, negation, and so on. Come up with a set of tests, evaluate the models quantitatively, get some checks and crosses, checklists on multiple criteria, and figure out that you have a good solution. The question is, how do you create these tests? And what's a good methodology for doing this? This is what we worked on. Let me show you a few examples. They're very simple to kind of illustrate this. The first type of test you might do is meaning functionality tests, like short polarized sentences like I despise this aircraft should be polarized. Well, this was some small changes in negations, like a negated negative is either positive or neutral. These are pretty natural sets of simple minimal functionality that should always work. Despite being so simple and so natural, state-of-the-art systems and public APIs fail on this very simple test at rates of up to 15%. And with negation, they can fail at rates of up to 50%, illustrating that such tests can be very significant augmentation to standard test set procedures. Another types of tests are perturbations, like invariance tests. So for example, if I have a sentence like, thank you, I got a different flight to Chicago, and I changed Chicago to Dallas, then that's going to change the sentiment, yet public APIs and state-of-the-art systems fail at rates of up to 20%. While directionality tests, like if you add a positive sentence to a positive sentence, it should only get more positive. And nonetheless, tests like this fail at rates of up to 30% on public APIs. So what we propose is tools for easily creating and evaluating such tests. And we did a number of user studies with practitioners of real-world systems that are out there today in industry, and showed that using this methodology and these tools, they were able to find more tests, more test cases, and more mission-critical bugs on already deployed real-world systems. So to trust a machine learning model, we have to make sure it's competent. And competence and clarity are two aspects of trust that I think we need to invest more in and be more effective about. The third area that I think a lot about is alignment. Alignment is a state of agreement or cooperation between persons, nations, groups, with a common cause or viewpoint. And the key here is the common cause and viewpoint. In other words, does my model and I agree on what we're here for, what values we want to adhere to, what our mission is? When I was writing papers, it was pretty clear. The mission was showing that my curve was better than your curve. But there's a gap with that in industry that can be very significant. Netflix illustrated this very well a few years ago. They used to have this Netflix challenge competition about 15 years ago. It's pretty amazing, where the idea was, can you predict ratings of a user really well? But in practice, it wasn't particularly useful because the thing they really cared about was minimizing the chances that somebody would churn, they'll quit Netflix within a year. The problem is that that's really hard for a machine learning model to optimize. And so they found a better surrogate metric, which is maximize the chance that you binge watch something. So click it and watch it to the end and watch it some more. And they optimized that because it's closer to the business metric. This gap between the loss function, the thing the machine learning model focuses on, and the metric that you really care about in practice, it's significant and it's hard to bridge. You can find better loss functions like maximizing the probability of binge watching, or you can find better approximations of the business metric. They're easier for machine learning to work on. But fundamentally, business metrics are about multiple criteria that you care about and you trade off on. And fundamentally, there is not the same owner. Typically, a machine learning engineer works on the loss function, while a product manager maybe owns the metrics. And one of the approaches that we took on to address this gap is to take it more head on. So taking a parameterized loss function and then doing the regular iteration process of learning, measuring the metrics you really care about every so often, and use that to improve the parameters of the loss function be closer to metric. And this approach had significant practical impact in real-world systems at Apple, and generally illustrated this notion that having a better loss function closer to metric was fundamentally in practice. Most importantly, though, and ultimately, alignment is about alignment of values. Does the system that I'm building reflect the values that I want to bring to the real world? We've seen significant issues of algorithmic biases in machine learning having negative impact in the real world. And we need to do something meaningful about this. There are multiple criteria that are being proposed for how we address biases in algorithmic bias. And there are plenty of theorems that says these criteria are compatible with each other. But to me, fundamentally, what it means is that there are trade-offs that have to be made every day when we develop machine learning systems. And there's no good way for us to really understand and find the right trade-off points for many applications. And every choice that we make along the way in the creation of machine learning system has to be aligned with the values that we want to reflect in the world. Let me give you a grounded example of that. I asked myself the question, what are we teaching? What are we trying to teach as machine learning models? Maybe if I ask myself the question, what am I teaching my kids? So here are two of my kids watching a show that they love that I hate. It's called Paw Patrol. In this show, 6 puppies go on life-saving missions. There's only one girl puppy. She's always dressed in pink, watching on the sidelines while the other puppies go save the day. These are not the values that I want to reflect in my son or my daughter. And as we're experiencing the world more and more for devices full of machine learning infused experiences, we have to be careful not to perpetuate biases in the experiences we create. And every choice that we make along the way defines the decisions of machine learning models. It's not enough to just think about the diversity or coverage of data. We have to ensure that every development decision that we make reflects the values we want to exhibit in the world. Let me give you a final example of that. Take machine translation, which is an amazing task that's been completely transformed by neuro-machine translation. You can give a sentence like, how can you trust machine learning? And you get translations to hundreds of languages. But you have problems too. So for example, if you start from a non-gendered language like English and translate to a gendered language like Latin languages such as Portuguese and Spanish and French, if you go from the doctor called the nurse to say here Portuguese, you get the male doctor called the female nurse. And this reflects many biases in our society. Now, if you look at Brazil, about 57% of the doctors today are male, but the fraction of female doctors is growing rapidly. Now, if you have a machine learning model and you have data where, say, more than 50% of doctors are male, and you have to make a hard choice like you've done in this interface, every time, 100% of the time, you're going to say doctors are male. So even with infinite and representative data, you're not going to resolve this issue. You have to think holistically about the model and the application and how it will reflect the values and avoid the biases that you don't want to perpetuate in the real world. And every decision that we make in the creation of the systems is important. So I propose that through clarity, competence, and alignment, we can increase the trust and the positive impact of machine learning systems. Thank you for joining me today. I apologize for the earlier technical difficulties, and I'm looking forward to your questions.
Thanks, Carlos. This was amazing. Thank you very much. And thanks for letting us believe more in machine learning. We can now trust more machine learning. Just a quick question from my end. Wanted to just learn about where do you see machine learning moving in next 2 to 3 years? Very generic, but wanted to learn more about it.
Well, where's machine learning moving in the next 2 to 3 years? Machine learning is an incredible upward trajectory. Machine learning and AI systems are pervasive in the world. We're seeing them make a difference basically in every aspect of our society. I am personally pretty excited about the health space and really understanding how machine learning can help us live a healthier life through better screening, diagnosis, treatment, and delivery of care. I think these are areas where we've already seen some value in machine learning, but it's only the beginning. There's a very difficult technical, societal, and human challenges associated with care and the delivery of care, and there's significant disparities in different places in the world around health and healthcare. And so I believe that technology and machine learning, when well coupled with transparency and process change, can lead to better health outcomes around the world.
Awesome. Thank you very much, Carlos. This was a very insightful session. Thanks again.
Thank you very much. I appreciate it.
Yeah. All right, guys. Our second session for today, second keynote is by Dom Divakaruni and Peter Welinder. A little about our speakers. Dom Divakaruni is the group product manager with Microsoft Azure's AI platform, where he is responsible for services that help customers build the next generation of apps like GitHub Pilot, powered by OpenAI's GPT-3 and Codex models. Previously, he led product for AWS AI services like Inferentia and Elastic Inference and initiatives like Apache MXNet. Dom has a degree in electrical engineering from the University of Maryland. Peter Welinder, also about Peter Welinder, is a VP of product and partnerships at OpenAI. He leads commercialization of OpenAI's research, including OpenAI's GPT-3 and Codex API and the GitHub Copilot partnership. Previously, he founded and led applied machine learning engineering and product at Dropbox. He was the co-founder and CEO of Anchovy Labs, acquired by Dropbox. Peter has a PhD in computation and neural systems from Caltech and a degree in physics from the Imperial College London. Dom, it gives me immense pleasure to welcome both Dom and Peter. This session title for today is Powering the Next Generation Apps with GPT-3 Codex with the OpenAI API. Please join me in welcoming both our speakers today. Hey, Dom. Hey, Kevin.
Hi, good morning, everyone. Sorry, it took me a little while to figure out how to get off mute.
No worries.
Assuming you can hear me now. Sounds great. Let me also turn on my camera.
Dom, I also just made you a presenter.
Amazing.
Yeah, we can see you, Dom.
Let me know if you can see my screen yet.
Sure.
I guess not, huh?
Not yet.
Not yet.
Meanwhile, for everyone joining us, feel free to ask questions to Dom and Peter. We'll be having a short Q&A just after this session, so feel free to have those. Kuliana would be mentioning it in the chat section, so you can feel free to ask questions as they come to you. Yeah.
We actually can see your screen now.
Yeah.
Oh, you can. Oh, excellent. I'm gonna go full
You just
screen
need to
here.
present, I guess.
Yes. One second. Nothing like giving a remote keynote, but we just saw Carlos do it masterfully. So happy to, I'm grateful for this opportunity and happy to join you guys along with Peter. And thanks for the introduction. We'll cover in this session the state of the art. Like, where are we with machine learning platforms? Where are we with the tech that has led us up to this point to enable users to build applications with AI? We'll talk about where we're going and the sort of applications that the technology is currently enabling, and how folks can tap into it. So let's dive in. So, we just heard Carlos, but again, to touch briefly on AI, right? It's the ability of a machine to exhibit intelligence that it gains either via reasoning over potential outcomes to arrive at the right one, or to learn from past experience by internalizing patterns from data. So we've seen some great strides in the area of learning from patterns in the past few years. And these advances have made a meaningful difference in our everyday lives. From tasks like speech recognition, which is digital assistants, which has become a normal in every household, right, to meaningful applications that are making a real positive difference in human lives, like in the field of medicine, with the early detection of diabetic retinopathy or skin cancer. I'm an AI optimist, and I look towards an exciting future where there are perhaps no more car accidents, or AI supporting human research in developing cures for diseases. For businesses, AI is helping making a meaningful difference in practically every industry, automating processes and helping businesses delight their customers with new experiences. So let's talk about the cloud services that are making these capabilities and AI advancements available for companies and individuals to apply. So if you look at the major cloud providers, we'll see advancements in AI. They've emerged into roughly 3 categories of services for developers and data scientists. The first bucket of services are packaged end-to-end solutions like Azure Forms Recognizer, for example, which includes both computer vision and which is OCR, and language models to extract information from PDFs and documents and images. The second category are a set of APIs for specific tasks, enabling cognitive abilities in vision, speech, language, and decision. And lastly, we see powerful platforms like Azure Machine Learning, which have evolved over the past few years to provide practitioners with the tooling to build and train models from scratch and then deploy them in the cloud or optimize them for the edge. So if you look at the Azure Cognitive Services, for example, it has a wide range of APIs that are heavily optimized for specific tasks, right? And we are continually iterating to deliver the highest model quality and value for our customers. Altogether, there are about 30 or so domain-specific pre-trained models in vision, speech, language, and decision-making. These APIs support capabilities like machine translation, which are used by enterprises like Etsy to translate listings for various locales, and speech to text, which powers transcription capabilities for Microsoft Teams and Microsoft Office products. But as practitioners adopt these technologies for their own business scenarios, they find that they're faced with 2 choices between the straightforward set of APIs that you saw on the previous slide that are easy to use, but kind of just often fall outside the specific need of their business scenario. They don't quite fit the particular scenario that folks are going after. And then you have on the other side an infinite potential of ML platforms with a vast ocean of publicly available models that you could tailor for various scenarios. But that's just beyond the chasm of complexity and learning curve associated with open source frameworks, the tooling and expertise needed to manage the life cycle of iterative model development, and managing these models in production. Unfortunately, the expertise and time investment needed for these and kind of the leap of faith that's needed to head in this direction to adopt these technologies is out of reach for many. Fortunately, we've evolved a new kind of machine learning platform, the OpenAI API, that makes it easy to experiment, iterate, and then take concepts to production with a focus to start on language scenarios. So let's look briefly at what language models are to start and how they evolved to be so transformative. And then we can talk about the API service that's enabling this fast experimentation, iteration to production all in one, so folks don't have to cross the chasm. So helpful to set context, right? What do we mean by a language model? The simple definition of a language model is an AI model that has been trained to predict the next word or words in text based on preceding words. These models are applied for use cases like machine translation, extracting insights, classification, etc., and increasingly more capable scenarios like writing assistants and generating code, as we'll see Peter talk about. So these models have evolved over time quite dramatically, starting with techniques, statistical techniques like bag of words that have helped for use cases like document classification, but they were not really great for sequence modeling problems, as they didn't encode the information about the order in which the words occurred. These evolved into neural network solutions, starting with recurrent neural nets, which worked well on shorter documents, but they fell short as the documents got longer. So the RNNs then evolved to solve that longer document problem, but you ended up with these really deep neural networks that were super hard to train. And I guess the biggest challenge with LSTMs was that transfer learning didn't really work. So you had to train from scratch for various tasks. This made it quite challenging, but this culminated with the transformer model paper called Attention is All You Need in 2017, and several models that followed, the Muppet models as their famous Elmo, BERT, and others to follow. So the key advantage of these models is they're parallelizable. You can throw lots of data at them and GPUs to solve the problem and train these massive models. And we've seen staggering growth in the size of these models just in the past 2 years, right? With GPT-2 in early 2019, with 1 billion parameters, followed by GPT-3 with 175 billion parameters. And these are starting to grow like crazy. A key part of this journey, the real value is that transfer learning works, right? You can take a pre-trained model that was trained in a self-supervised way on lots and lots of data, and then you can easily fine-tune it for other tasks. And now the evolution is heading in the direction of where you can apply these models for new tasks just by providing it a few examples. And so that's what's really great about this evolution, is that you can now start to use these models for various tasks than it was originally trained for, and just by providing it a few examples. So let me turn it over to Peter now to show us some examples on how this works.
Thank you, Dom. Unfortunately, I can't show my camera due to some technical difficulties. So, but you're probably better off that way. So let me talk a little bit about kind of GPT-3 and kind of the idea of programming with prompts. So as Dom said, GPT-3 is this 175 billion parameter language model that is where and our API kind of makes this available and Descendants available. And it's these models have been trained on vast amounts of text, basically, as Dom said, like taking some text and predicting the next word. And it turns out that you can, when you train a model that way, you can apply it to a vast amount of different use cases. And the way you kind of program these models to apply them to different use cases is basically by creating prompts. So here's an example of translating an email into my native language, Swedish, from English. And the way you basically get the model to do it is basically by just asking the model to do it. And so what you see here in boldface is the prompt, and what you see below it is the completion, what the model kind of returns after you provide it with a prompt. So to get the model to translate, it's as simple as just asking it. But that's just like one use case, and there are many more you can do. So I'm going to go through a few different ones. There are simple ones, like, for example, grammar correction that kind of require dedicated models in the past, and GPT-3 is like excellent at it. So let's look at one example here where you just kind of ask the model what to correct grammar by, say, basically here we just tell the model fix the grammar in the sentence below, and the model improves the grammar of the input sentence. And I think the important thing here to kind of make clear is that we haven't trained the model specifically for these use cases, and there are different ways you can input the same instruction. So here's a different way of telling the model to do the same thing. Like, the model is very robust to different ways of asking it to do different tasks, and so you don't have to necessarily fit your instructions into a particular pattern that we have kind of pre-trained models on and so on. Again, this is all learned by basically training on vast amounts of text that available on the internet, essentially. So this is like one simple use case. let's move on to look at a few other use cases. So data extraction is a pretty common use case, and GPT-3 really excels on this. Like, here's a simple example where you may just want to extract, say, an address from an email. Again, you just ask GPT-3 to do it. Extract the mailing address from the following email, and GPT-3 kind of just does it. Like, if you want to kind of have a more structured output, it's simply about like augmenting your instructions a little bit. So if you look at the next example here, we kind of lead GPT-3 towards segmenting the address into kind of street and city and zip and so on by simply kind of adding that adding street below the address. It kind of picks up on that pattern. Like, it's really good at this pattern matching, and it kind of picks up on this pattern and then segments out the address for us. Again, all by just kind of providing a simple instruction. So these are kind of more kind of old school in some way natural language tasks, but you can do more kind of interesting things. So if we move to the next, here's a fairly tricky example where here it's a piece of text about kind of a made up planet where there are some different fruits of different colors and different tastes. And we want to kind of extract that information in a kind of more structured way. So we simply ask GPT-3 to summarize that information in a table, and a bunch of things is happening here. Like, GPT-3 picks up on the pattern of that each of the fruits have different colors and tastes. So it creates actually the headers of this table itself, and then it picks up on all the different attributes of these fruits. Even though the order of how the fruits and the colors and the tastes are mentioned kind of vary and so on, GPT-3 kind of is able to kind of deal with that and create kind of a summarized table and stop when it's kind of done summarizing all the fruits in that passage. Again, just from kind of having learned how to do this by just looking at tons of different tasks on the internet. So so those are kind of some data extraction use cases. Let's move on and look at some kind of new, some really interesting kind of use cases of GPT-3 where we've seen a lot of customers apply these models, which is really about aiding human creativity. And one of the ways you can do that is basically having GPT-3 to kind of provide kind of examples or ideas for you. So for example, if you were to interview a science fiction author and you were thinking of like, what should I ask this person? You can ask GPT-3 to kind of create a number of questions for you. What is really interesting here is like it kind of serves as kind of a brainstorming partner or like a writer's block. It kind of really helps you come up with ideas. You may or may accept some of them, and you might reject some of them, but it kind of gives you a starting point to work from, and it can often put you in really great directions. And there's multiple kind of actually authors out there that have written whole books at this point by working with GPT-3. And so the last example I want to show here is a similar one where it's a little bit more complex in that you might want to have a specific output format. So if we move to the next example, here's an example of kind of generating product names. And if you have a particular pattern that you want GPT-3 to kind of pick up on, you simply kind of provide one or two examples of the format that you want, and then GPT-3 is like able to pick up on that format with like just like one or two examples. Like it's really kind of few shot learning here. So here's an example of creating product names for shoes that can fit any foot size, and they're actually pretty good names. And this kind of allows it's a whole new kind of use of language models that just wasn't possible before. So anyway, so this is like the kind of the different ways you can use GPT-3. A lot of different use cases, and this really only touched a few of them. We have a number of customers who are at this point building on top of our API. Here's just a few of them, and here's kind of a testimonial of Duolingo who's using it, for example, for translation, where it works really well. Okay, so that's sort of some of the breadth of use cases. Dom will talk next about a little bit how you go to kind of production with these models.
Gotta get myself out of mute. Thank you, Peter. That's a really neat set of demonstrations on how you can apply the same model with the same API for various use cases. And it's a standard API, right? Which is a departure from the past where you had bespoke API for each task. Here you have a generic API that you could just apply just by providing it instructions. So the platform that brings all the various GPT-3 models, and as Peter mentioned, there's four different ones of different sizes based on the complexity of the use case. So democratizing these models is and helping users really cross the chasm is a powerful AI software platform called the OpenAI API, which makes the technology incredibly accessible, right? It unlocks creativity with easy experimentation. It lets builders go really non-developers to ML experts, right? Go from completing a compelling prototype in 5 minutes to scaling customized models to production level loads. The API's simple text in, text out interface lets you apply it to any language tasks, as you saw, or code task by showing it just a few examples. The possibility with this is, like, imagine if anyone in your company, regardless of the programming experience they have, had the ability to bring their creativity to life with a proof of concept in a few minutes, sort of illustrating the art of possible before you have to make a costly decision to fund a project, right? And then once there are signs of life, once the idea clicks, then you can fund the project with development resources to really take that into production and integrate that into applications. It really unlocks innovation for enterprises in quite a meaningful way. Once you have a proof of concept, then the API makes it easy for developers to customize the model accuracy for a particular scenario. It's without a steep learning curve, and in a way that it makes it accessible to all developers. So let's look at that a little bit. So the API helps you develop concepts quickly and then provides you with the tools to scale applications in production. So in this example, the user simply states the objective of the task, which is to summarize game commentary. In this case, it's a WNBA game. And the simple task to the model is to summarize game commentary, and the model produces a response. And this is kind of what Peter showed you. This is called zero shot, the technique, and it tends to be accurate about half the time, but it's very effective for prototyping ideas quickly. So to take this to the next level, you provide the model with a few more examples of the type of summary that you're looking to see, and then the model generates outputs that are more reliable for a number of inputs that you provide. So here you're starting to improve the quality of the model with the few shot technique to build upon the quick experimentation with zero shot. And then finally, to take this iteration journey into production and optimize accuracy and latency, the next step is to fine-tune the model with labeled data to really improve the accuracy and latency. The API makes it easy to submit a fine-tuning job and then deploy the model into testing, deploy the model for testing and production. So let's walk through a quick example of what fine-tuning looks like. So this is a super simple example where we're optimizing the accuracy of the model to classify between two sports, baseball and hockey. We're using a publicly available scikit-learn news group labeled data set. It has emails sent to various mailing lists on labeled for different subjects. The data set really has 18,000 examples in some random categories. So we're going to just peel back the ones for baseball and hockey, and there are about 1,200 of these, right? So we're going to load these examples into a data frame and label the columns as prompt and completion as the fine-tuning API expects. And then we'll export this into a JSON-L file with lines delimited for each example. Then OpenAI provides a handy data prep tool which suggests improvements to condition the data set for training, removing longer examples, for example, or adding white spaces to make it more suitable for the tokenizer. the tool also detects that it's a classification task and suggests the command to enter to fine-tune the model with this data set. And it suggests the hyperparameters that are suitable for the use case, and there are several such presets that are available. And the model, the script also suggests that you use an ADA model, which is most efficient and fast for a classification task, and sufficient for a classification task. Then when you execute this command, in this case, the job runs for 4 epochs, and it takes about 10 minutes to complete. And then you can export the results to a CSV. And when you view the results in your notebook, accuracy in this case reaches about 99.6%. Now, all you have to do at this point is call OpenAI's completions API with the name of the fine-tuned model and a new prompt. And in this case, we use log probs as well as a parameter to see the probability for each class. And this model has been trained on emails, but it generalizes easy to other types of tasks like tweets, for example, and still produces accurate results for classification on different types of data. So let's Peter, if you can walk us through now what are the more recent innovations with GPT-3, with OpenAI past GPT-3?
Yeah, thank you, Dom. And it's really, GPT-3 is kind of just the start here. Like, we're continuously evolving kind of the family of models that we make available in the API. And this summer, we actually released a new model called Codex, which is basically going from natural language to code, which opens up a whole new series of use cases. And we actually developed this based on that we saw a lot of people using GPT-3 to do coding-like applications. So we're a bit short on time, so I'll kind of breeze through a lot of these examples. Similar to the previous examples, you provide it with a prompt, and in this case, you provide basically with a comment in Python, and the Codex can produce Python code. So in this case, creating both a list of names to kind of first name and last names, and then producing the code to kind of generate combinations of that. So that's a pretty simple example of how you can go from sort of text to code. If we go to the next example, it turns out that the Codex is really good at using a number of different APIs because it's been trained on lots of code on GitHub. So this was developed in partnership with GitHub. And so in this previous example, you can see it's kind of using the Stripe API quite accurately. The next example is just to show that you can generalize to different languages. Here's SQL, so it's a pretty complex query you can get out by just describing the table names and so on that you have. And Codex is able to kind of create the SQL code to make that query. So those are kind of some just kind of text to code examples. You can actually go the other way, where you can, if you have a complex piece of code and you're like too tired to understand it, you can ask Codex to explain it for you. So here you're creating a doc string that that kind of explains this piece of complicated code. And if we go to the next example, you'll see it kind of being applied in an even more general way. You're basically creating a little chatbot that you can talk about JavaScript with by, again, just kind of creating a prompt of a conversation of you and an imaginary kind of JavaScript chatbot. And the model picks up on that and is able to kind of ask questions about JavaScript. So that's like just a few use cases of how to use Codex. Generally, there's a lot of different things you can kind of use Codex for. The way we look at it is like you can use it to kind of make your APIs more accessible. You can accelerate software development. For example, we've done a partnership with GitHub where we have GitHub Copilot, which is basically a coding assistant built on top of Codex. And then generally, we think that Codex really can widen who can code by lowering the barriers to coding. Like suddenly everybody has kind of somebody, a coding assistant that can guide them through coding and so on. So anyway, the future here is that we'll get more models that can do even more things. And to wrap it up, and I'm gonna hand it over to Dom now to wrap this up.
Yeah, thanks, Peter. It's pretty compelling what Codex can do, and I can't wait to see what customers build with it. But these APIs and models they provide tremendous capabilities, unlock new scenarios, and can enhance human productivity. But it's super important to us that they're applied with safety in mind, to ensure that they're only applied for good, and applications that leverage the API have the proper mitigations in place to make sure the technology isn't abused for malicious purposes. So our approach here is threefold. First, we work closely with customers to support them with tools like content filters to detect whether the generated text is safe or not. We're iterating quickly between Microsoft and OpenAI to develop additional tooling for our customers to tailor the tone and topics of the content that the service produces. Second, the service monitors abuse to help customers ensure that the system that they build, the application that they build, is only used for its intended purpose. And third, and perhaps most importantly, we're working with customers to help them design applications in a manner that puts quality and safety front and center. We're partnering with customers to help them get their apps to production. Our safety experts then conduct a pre-production review before applications go live to assess the potential for abuse and determine if the risk mitigations that they have in place as these applications scale are successful. We'd actually like to invite you to join our event on, a little plug here, on Tuesday, December 7th, to discover best practices from our experts on how to build AI solutions responsibly. And the service is made available via the OpenAI API, as we've shared, and via the Azure OpenAI service, which we just launched recently at Ignite this month. The OpenAI API is the best place for customers to get started with exploring the use cases and taking applications to production. And as enterprises expand their applications with business critical use cases, the Azure OpenAI service can help them scale with enterprise grade security and compliance. The service is built on Azure's global cloud infrastructure, meaning that it can support toughest production requirements around scale, regional deployments, security, compliance, and reliability. So to learn more, I invite you to visit openai.com/API or azure.com for the Azure service. Here are some useful resources and documentation that you can refer to on how to use these capabilities. And we can't wait for you to use this in various meaningful ways for your business and see what you can accomplish with them. Thank you for joining this session. I'm happy to take questions if we have time. I'll leave that to